Welcome everyone to the second lecture of string theory. I don't know why I did this. But today we're gonna continue with special relativity. We're gonna start reviewing all the stuff we covered last class. And I wanna clarify a lot of stuff, so there's gonna be two parts for this video. There's gonna be first all the review stuff that we're gonna do. And second, we're gonna start with Lorentz transformations and classical strings. So that's what we're gonna do today, and let me change the scene. I'm a streamer, let's go. Okay, so I'd want to review a couple of things. So in order to review this, let me do a very intuitive examples. Like this is gonna clarify all the physical intuition for special relativity, like why time dilation happens, why space contraction, that kind of stuff. So first, let me draw a car. Let me put a person here. Place A, and now let's shoot a pulse of light from one mirror to the other. Let's say this is a mirror and this is another mirror. So let's have going up, going down. Yeah, we don't need the lower mirror, but you know, it's just there. Okay, good. So this is in the perspective inside the train. So now let's say the train is moving, and then there's a person that's looking at the train. So from B or Bob's perspective, the train would be moving, or like the pulse of light, instead of like being up and down, it will be doing something more like a triangle, something like this. You've taken 202 or like any other special relativity class. You probably already seen this example like 10 times, but bear with me, or you can escape this part, like if you know all the special relativity. Yeah, good. So let's give this a length L naught, and then let's give this L naught. And then how much is gonna move? Let's call this the speed of the train times some interval. This interval, delta t, is going to be in Bob's frame, and let's call that delta t naught in Alice's frame. Why are we calling this? It's going to make sense. So this one is very simple. We're going to count only half, like only how much time it takes to go from the bottom all the way up. So how much it takes is just L naught divided by the speed of light. Why? Just the distance it something travels is like the speed, distance over time. So just replace it, move time around, and then you get that. Cool. Okay, so then we can do Pythagorean theorem here. We know that a pulse of light has to travel at the speed of light times some time interval, and this is going to be the same time interval that the train is going to move in this first part of the triangle. So we get c squared plus, we get L naught squared plus b squared delta t squared equals c squared delta t squared. Now let's do some algebra. We get squared c squared minus b squared equals delta t squared. We're gonna take square root and then take out c squared factor. So that's gonna give us L naught then c square root c 1 minus b over c. Okay. And then you notice how this thing is the same as this thing here. So you can just replace it. And then we get this. T naught divided by 1bc. We're going to define this as something that you're going to use all your life, and you're going to see it everywhere, called Lorentz factor, or also gamma factor. So we just define 1 over the gamma factor is equal to this. So just to remember, like the gamma factor is going to be this. You're going to have to memorize, sorry, I'm missing a square here. Okay, it's going to be this always. And what this is telling us, if now we replace the gamma definition, is that from the rest frame, or like inside the train's frame, to outside the train, like someone that's standing outside of the train, this is gonna look like the time has dilated, because this factor, you can prove it, that is always greater or equal to 1. And yeah, something I forgot to say that's very important. I think I recorded this lecture twice, because the pre-recording got erased because I didn't have memory. Now I erase stuff, and it's gonna, hopefully, I don't have to record this a third time. So the two possibilities for special relativity, like if someone asks you what special relativity is, you just have to say two things: that there's a constant speed, like maximum speed, that nothing else can travel faster than the speed. That's called the speed of light. Speed of light in vacuum, but yeah, they're like, it's constant. It's just maximum. It's constant in any frame. And the second is that the laws of physics, like the form of the laws of physics equations, is not modified by different frames. So physics, the laws of physics are gonna work the same way, like the same way in different frames. That's gonna make sense. But the laws of physics don't change by reference frames. Laws of physics don't change by the frame. Sure. Okay. So these are the two things, the two postulates that we're gonna use. And here, as you notice, we used the first one. So yeah, that was a very important step. That C is just constant. It's gonna be the same in every frame. Doesn't matter of whether Alex or Bob is seeing it. And here we get time relation. And then you can believe me if you do a similar example, but instead of having this card like being up and down mirrors, then you can try by yourself doing this example. There you have mirror here, you should have pulse of light. And you can do similar algebra and find that instead of time being dilated, the length is being contracted. So you're gonna get L0 divided by a factor. And this is like contraction. So this is the funny thing in special relativity. Well, by keeping one constant, something constant as the speed of light, then we get that space and time have to change. They have to be dynamic things. And that's gonna lead to a whole lots of stuff. And eventually general relativity and eventually string theory stuff that we're gonna derive from that. So fun stuff. Funny fact, if people had discovered string theory before special relativity, or before general relativity, you could have derived general relativity from string theory. And we might see that if there's time. Okay, so great. So that was the example I wanted to give for the physical picture that I wanted you to have in mind for special relativity and why it makes sense to talk about like time dilation, space contraction, and interstellar, that kind of stuff. And I'm gonna go more much in detail. So now I want you to make sure that you understand these things, and I'm gonna review them. So let's start with 4 vectors. Oh, let me give you just like a top down, and then we're gonna do bottom up perspective. So top down, we're gonna start with a more general, like why we care about this stuff and like why the heck we're doing special relativity. So we have like strings, right? So we want to make these strings go very fast because that's what happens in like special relativity. Or like not necessarily fast, but like any speed, can go any speed. And then we want to quantize, I don't know why I draw your errors, I don't know, they're just fast. And then we want to quantize it. We don't know what quantize it means yet, but by quantize it, it's going to mean something. And that means just going to the small scale and see what happens. So that's going to be actual string theory when you have like, yeah, let's just call it that they become small strings. And this is all going to lead to a bunch of stuff that we covered in the first lecture, introduction, like why we care about string theory, because it gives us a lot of degrees of freedom. Instead of having point particles that are like 0D and they can move like this way, go up, and like X, Y, and Z, then a string can do like much more stuff. You can make knots with strings, you can make anything with strings. Like the whole reason string theory kind of works is because you have so many degrees of freedom, and then that allows you to describe like complicated stuff, such as space-time. And that's the reason we care. So that's the first thing. And we care about all these tools because this is going to be like our main toolkit to describe the equations of string theory. So make sure to understand these different sections. So 4 vectors, I'm just going to say a couple of things that I probably said already. A 4 vector, let's think about first a 3 vector. I think shout out to Raul who gave me this explanation. That is like probably the most easy and fast and intuitive. So you have a 3 vector. You know a 3 vector, it's just 3 components. So now imagine adding a 4 component. This is not in 3 dimensions, but doesn't matter. So a third component, that's gonna be time. Okay, that's a 4 tuple. Not necessarily a 4 vector. We're not gonna define about exactly like what is the difference between a 4 vector and a tuple is for now. It's gonna become later. Okay, so this is, let's say this is a 4 vector. Any 4 indices object I'm gonna give you in this class is gonna be a 4 vector. So, okay. So for example, for position, instead of having like the position vector, we're gonna have a position 4 vector that is gonna include time. And it's gonna be defined by minus, so like by ct, x, y, and c. Why the c is because we want it to have the same units. We want to have space units, so great. Okay. So that's our 4 vector that describes space. That's just a spatial 4 vector. And there's gonna be another thing that's very important from 4 vectors, that is the invariant interval. Fancy name. Think about the modulus. So let's think we have a normal vector, we do the dot product, and usually whenever you do a dot product, what you're doing is just you're adding components. Let's say x, y. We do this dot product, doing x0 plus x1, y1 plus x2, y2. All right. Let me make the indices more clear. Okay, 1, 1, 2, 2, 3, 3. Something like that. We usually do that for dot product. Is it right? Yeah, this is right. Okay. Something even more intuitive. You have this x component plus y. Like we have, I don't know, some vector. X, y, c squared, squared. So that's the modulus of a vector. If I'm doing everything correctly, just Pythagoras, just take a triangle. And imagine now adding a new component. Now we're adding time. And why it should have a minus sign? Because we're gonna see it has a minus sign. It has to have a minus sign because whenever you do measurements, like nature just tells you it has to be a minus sign. Like if you try a plus sign, it doesn't work. But if you try a minus sign, it works. So cool. So technically these are gonna be like pseudo vectors. Don't worry about that. Just remember that a 4 vector then is gonna have this invariant interval, or also just the modulus. And we define like this. By the components, x naught square plus delta x1 square plus delta x2 square plus delta x3 square. Right. So okay, so the signs can differ depending on the convention, but we're gonna use this convention. Don't worry about conventions. That's gonna come later. That if we change the convention, I don't think we're gonna do, but it's good. So basically this interval encodes distance, and like as you have distance between 2 points in space, let's say this is xy, right? X and y, and this like has some modulus, or like some distance. Then you can also encode distance in space-time. Just add 1 more component, and then maybe 2 more components if you want to like describe the whole thing, something like that. And then you get a 4 vector. 4 vectors in the space-time. Something important to mention that I forgot to say about 4 vectors is that any point, let me draw this diagram, x1. So this is a space-time diagram. It's just telling you coordinate of space and coordinate of time. So here, if you have a point that's called an event, it's just any point, like something that's happening in reality, described at some space and some time, then you put it as a point. That's just an event. And like there was a big misconception that I had to clarify from last class. It's about time-like vectors and like vectors, space-like vectors. So, intuitive rule, the most simple thing. If it is, let's draw a 45 degrees line from like any point here if you want. If you have another event that is here, or that is here, or that is here, so whatever it's in 45 degrees, it's called light-like separation between these 2 events. Between these 2 events is a time-like separation, where it's about 45 degrees, and like it's like inside this light cone. And less than 45 degrees is space-like separation. And now, the physical picture, like why we care space-like, time-like, like what the heck's this? What's going on? Let me give you a good explanation now. So, let's go to this interval that we wrote here. And we can put it in this form, c squared plus delta x1 squared. and there should be a delta here. Okay. So let me show you something. So for light-like vectors, or like for time-like vectors, this means just like doing this and this. So by that I mean you have some event that happens at a time, you wait, something else happens at the same time. Let's say this is our two events. How can we describe that in this graph in a beautiful way? Then we just put a point. Let me erase this. And we didn't change position. We did like the two snaps in the same position. So it just advanced through time. So one snap, second snap, snap one, snap two. This is how we describe stuff in space-time diagrams. And you can do now space-like. So we do this at the same time. They were the same time in my frame, but they happen in different places. So we call this space-like. So that would be like, this is the first snap, and this is the second snap. Cool. And they would have a space-like separation. And light-like would be me just shooting a pulse of light. Like let's say there's a light here, and I'm here. So I shoot light, it arrives at some point. And how is that described? It's just gonna be a 45 degrees, because the speed of light doesn't change, so it's just gonna be the same. And now, let's do the math. Like why this makes sense mathematically. Imagine we have any point that is above this line. Let's say here. So you believe me that this separation here is gonna be greater than this separation. Like, let me draw it even more exaggerated. Something like these two events. Let's draw a line. Then you can do a triangle here. So the biggest separation is going to be time, and the less separation is going to be space. That's going to tell you that whenever this thing, this is going to be small, or this is going to be big, and this is going to be small. Therefore, this is going to be negative, this side, and then therefore this thing is going to be positive. Just take the minus sign. So whenever this interval is positive, we say time-like, and then you can do similar whenever this is less than 0, it's going to be space-like, and whenever it's equal to 0, it's light-like. Okay, why is this true? Because let's say you draw a 45-degree angle. This is for light-like, and then you can imagine your triangle between these two events is always going to have same base and same height. I don't know how you call it, but yeah, these two sides are going to be the same, so it just cancels whenever we do this calculation for the invariant interval. Yeah, that's cool. So the invariant interval is something that doesn't change when you change frames. I think we showed this in class. If we didn't show it, it's in the notes, but it doesn't change. If you take two different frames, the invariant interval is not going to change. So that's what matters. Cool. Okay. Next thing, let's see. Okay, we checked this one. Now the invariant interval doesn't change. Is described by this. Let's say we have a frame S and a frame S prime. Whenever we write the prime, it would just mean the other frame. Then this stays the same. Cool. That's the whole thing. Whole thing you have to remember. Now let's go with a space-time diagram. We covered that already, and then Einstein notation. So Einstein notation, that was a big confusion. It's much simpler than it seems. You just have to get used to like how it works. There's two rules. First rule, there's gonna be two indices and only two, like exactly two the same index, like the same index. But let me show you what it is first. Like whenever we write, let's say we have, this is a 4 vector and this is another 4 vector. And we do this notation. This is the same as writing the summation from 0 to 3 of x mu, x nu. And essentially this is just, if you extend the components, then you're gonna get minus x0 plus x1 plus x2 plus x3. Cool stuff. So rules, the same index can only appear twice. Like it has to be exactly twice. Very important. And then one lower and one upper. Like one lower index, upper, like exactly one upper and one lower. Yeah. So some examples to make sense of what this actually means. Let me go here. Okay. So let's say we have two random 4 vectors. There's an A mu 4 vector and we have B mu 4 vector. This is the same as just saying this, as we wrote above. I hope this makes sense, and this just means just write out the components. If you ask me about that minus sign at the front, I'm gonna ask that question when we talk about Minkowski metric, but this is the convention. Good, and then you know how it goes. Okay. What else? Then some things that cannot be summed over are, for example, something like this. We do C mu because there's 3 indices, so this is wrong. This doesn't make any sense. Then what else is wrong? Then something that is not wrong, but is not Einstein summation convention is this: A mu plus B mu. Here you're just simply adding one 4 vector to another 4 vector, and you're not summing over anything. You're just adding 2 4 vectors. Yeah. So explicitly that would be like 0, 1, 2, 3, and you can imagine we're just gonna add the components. So yeah, that makes sense, right? Okay, cool. What else? Something else is wrong. If you do x mu, like a 4 vector, another 4 vector, they're both lowered. That's bad. Don't do that. This doesn't make sense either. And what else? Yeah, that's it. So this allows us to write our invariant interval. This interval that we had here, we can write it in differential form first. It looks like this. Dx. Wait, let me write it here. Okay. X0 plus dx1 squared plus dx2 squared plus dx3. And if you follow the Einstein convention, then it will just give you dx mu, dx nu. Cool. It's a very compact way to write stuff. Einstein was very lazy. We are very lazy to write all the components and like write summations signs. So yeah. So that we know how to write this, we just write this. Cool. That's Einstein notation. Okay. So now the Minkowski metric. I told you about the minus sign that is here in the first component, and where it comes from, let me show you. So Minkowski metric. Okay, so this is gonna make more sense with an example. First, the Minkowski metric, we can describe it by a matrix. It's just this matrix that is -1, 1, 1, and then there's a bunch of zeros here. Cool. Okay, so you can imagine if we're gonna define the lowered component of a 4 vector to be just this thing multiplied by the upper component. A very fast way to see why this makes sense is just doing this. And then you do x1, x2, x3, like a column vector. And this is gonna give you a row vector. So whenever, if you wanna think about, there's 2 ways. One, you can call this fancy name that this is called a contravariant vector, 4 vector, and this is called a covariant 4 vector. Or you can just call it upper index, lower index, and then whenever you see upper index, column vector, whenever you see lower index, it's a row vector, as usual. So this would give you that minus x, x1, x2, x3. Just do the multiplication, you get that. Okay, so essentially the Minkowski metric, this is called the Minkowski metric, just allows you to raise and lower indices. Its inverse is just gonna be the same thing. Just the same matrix, but instead of lowering the index, it's gonna raise the index. Cool. An example of this. Let's say we have our 4 vector b, I'm forgetting Greek letters, b nu, I think. And then we wanna lower the index, so you can multiply it by Minkowski metric that has the same index. So these are gonna like cancel, and then it's gonna be lowered. That's a very easy way to remember how it works. Cool. This is true. You can show it. And I had an example here. Oh, the example, the quick exercise that I showed is wrong. You can tell me why, because this is how I wrote it. And there is one thing that is wrong here. This is your mental exercise. See what is wrong here. 2 seconds. Okay, so there is 3 indices. My bad. Okay, so that's how the Minkowski metric works. Let me show you how we can raise indices. Let's say we have a random 4 vector, but it's lowered. And then we can raise this index just multiplying by this matrix, and this is gonna give you an NU. You can also do this with multiple indices. So let's say you have some object that has t, mu, and nu. This is actually gonna be an object. And then you can lower one of the indices by doing like mu rho, and this is gonna equal, you can imagine, rho nu. Cool. So you can lower raise. There can be one lower than one raise. That still makes sense. And they just have like, yeah, they just change what the position of the indices is. Another important fact for the Minkowski metric is the following: that if you multiply a new, like this, where's this? Here, I think, yeah, it's just this, if I remember correctly, yeah. You have, let's say, mu rho, and then the inverse rho mu. This is just gonna be equal to the Dirac delta, mu nu. Okay. And this is the same just as identity matrix. So it's just gonna look like this, 1, 1, 1, 1. You can multiply these two matrices. This is a matrix, like, yeah, you're summing over this index. So whenever this happens, you can do this. You can contract the indices, and then you get a Dirac delta, which is equal to the identity matrix. So cool. This is a useful identity. We're gonna use it very soon for the lecture. And I think we're done with all the stuff we had to review. Oh well, we have to review dot product very quick. So the dot product, now that we have the Minkowski metric, so this is just two very friends that you have to remember. Ask me if this part didn't make sense, ask me, because it's very important. Einstein notation, have two indices, cool, that makes sense. Second friend, it's gonna be the Minkowski metric. You can raise and lower indices. We're gonna use it all the time. And the final thing, the dot product. If you have 2 4 vectors, let's say 4 vector, you can write like this, or you can write it like this, just like without the indices. People write it like this. The definition is gonna be a0, b0 plus, there's a minus here, a1, b1 plus a2, b2 plus a3, b3. Or also, we can write it like this. Cool. Okay. And I told you about the minus sign that is here, and it's also here, and it's everywhere. So why is that minus sign? A very easy way to see how it appears is just from the Minkowski metric. So whenever you have the Minkowski metric, it's a -1, 1, 1, 1, and you want to multiply, or you want to like add up these two matrices that are just column vectors, you can see that there's going to be a minus sign, because these just have like components. These components, b1, b2, b3. You multiply stuff, and it makes sense that there's going to be a minus in front. There's conventions in which instead of minus, this is plus, and all of the other ones are minus. That's the second convention we're going to use in this class, but you probably will see it. If you take a field theory class with Professor Long or other professor, you might see that. So cool. So that's how the dot product works. The definition, this one. We're going to use it all the time again. So cool. Okay, so this is all the stuff we had to review. We did the physical intuition of like why special relativity makes sense, and all the math. 2 things: Einstein notation, summation, like summation convention, and the raise and lower stuff. I can repeat that like 10 times, but it's okay. It's necessary to remember. Okay, so this 29 minutes review, cool. Now we're actually gonna start the lecture. So if you skipped until this part, we did all the review of special relativity, just a quick review. And now we're gonna continue the lecture. Okay. So now let's get started with the second lecture. For the second lecture, we're gonna do today more Lorentz transformations, and we're gonna start classical strings. And the goal, like why we care about this, let me put like the goal for today. Oh my god. Okay. Okay. So the goal for today is gonna be first Lorentz transformations. We're gonna do classical strings, which this implies learning Lagrangian mechanics. This also implies Hamilton's principle. And some calculus of variations. This is gonna be extremely important, and it's probably gonna take most of the lecture to do calculus of variations. Sorry. Okay. So why we care about all this stuff, Lorentz transformations? Because we want to know how to move between different frames, like from a frame S to an S prime, and like see how our stuff changes. Why we care about classical string? As I said, we're gonna go from classical string to relativistic string, and then from there to quantum relativistic string, which is actual string theory. Like once we get there, that's gonna be in 2 lectures or like 3 lectures. We're actually gonna start like seeing quantized relativistic strings. So great. That's why we care about classical strings. It's gonna be a simple example that's gonna give us some intuition about normal strings. This is just the strings in real life. A cable is a string, that kind of stuff. It's gonna be a classical string. Okay, so let's get started with the first thing, which is Lorentz transformations. Great. Okay, so let me assume that either you've taken 202, which I know more than half of you have done, and the other option is that you have watched the previous 20-30 minutes of the lecture. That was just a review, and in that review we did an example in which you probably already know the example. Like you have a card, you have a person, and then you have this is A, this is B. This person shoots a pulse of light up and down, and we get Lorentz transformations from there. We get very simple ones, and if you trust me on this, that you can generalize the Lorentz transformations that we saw at the beginning of this lecture, and you can write the following. These are 1D boost Lorentz transformation. I'm gonna comment a bit on this. Let me just write them down. They're not gonna be super important, it's just to make a point. We're gonna make a important point about Lorentz transformations pretty soon. Okay, so first, what is a boost? So a boost, let us imagine the following situation. Let's say we have one coordinate system, like we have y and x, and then let's say we have also y and x, but this other frame of reference is moving with respect to the other one. First, something you're gonna see all your life is the beta factor. It's just defined as the velocity of this frame divided by the speed of light. Just makes it easier to write stuff down. Good, I think we saw it last lecture, but if we didn't see it, then here it is. Okay, so imagine this situation, we have one frame, the other frame is moving with respect to the other. So this moving with respect to the other is what we call a boost. This is essentially a boost. And you can boost between frames. If you want to go from your frame to another frame of reference that is moving with respect to this first frame, then you can boost and do a transformation. And this transformation is Lorentz transformations. And specifically for a 1D in the x direction, the Lorentz boost is like this one. Good. So trust me that you can derive these formulas. I think I put the derivation. Yeah, I indeed put the derivation in the notes. Pretty long. I'm not gonna go through it. We don't have that much time. I don't wanna extend this lecture to 2 hours. Okay, yeah, it's already a bit long, this lecture. Okay. So with that said, also just remember this. We're gonna use it all the time. B squared or C squared. That is the gamma factor or Lorentz factor, which also can be written like this with the beta factor. Very pretty. It makes it easier to write stuff. Cool. So why we did this point of just showing you the Lorentz transformations? Because we can generalize them more. We can generalize them to general matrices. So what is the general definition of a Lorentz transformation? Which essentially Remember, Lorentz transformation just changes you from one frame to another frame, and it tells you how things transform. So in general, let me put definition of Lorentz transformation. Lorentz transformation. In general, a Lorentz transformation are invertible, linear, these are the conditions, linear transformations of coordinates. I'll show you what that looks like of coordinates. And very, very important. Well, there are these two things like invertible, linear, but most importantly, that respect our inequality that we know. Our equality of square and this. Okay, so when the invariant interval is invariant when we change Lorentz frames, and the way that we put this mathematically is by Lorentz transformations. So any Lorentz, like the definition of Lorentz transformation, invertible linear transformations of coordinates that respect this equality. Good. So that definition made precise. Now we can write, whenever we write four vectors, changing from one coordinate to the other. Like let's say we have some four vector, and we want to see like how it relates to another four vector in like the same four vector but in another frame. Then you're gonna multiply your first four vector by a Lorentz matrix. Let me make this more pretty. Okay, so that's just it. It's just a matrix. That's gonna multiply to your four vector, and it's gonna allow you to transform between frames to go to another reference frame. Great. And for example, now why we did this example? Okay, great. So imagine this L mu nu is equal to this matrix. Minus beta 0, 0, 0, 0, 1, 0, 0, 0. Cool. So if we multiply this by our four vector, we get the following. You can see from here, we get the first component, it's gonna be x naught minus x1. This is just time, so wait, let's see. Let me put it like this, plus x1, and then the other two components are just gonna be the same, x2 and x3. Cool. And what is this? This is the transformed, the transform for vector. So as I told you, the Lorentz transformation is just a matrix that when you multiply it, it's gonna allow you to transform between frames. Cool. And as you can see, these are the same. I'm not sure if you can see it very well. Yeah, I think it's you can see it. That it gives you the same result. And I think I forgot a beta factor here. Cool. Yeah, it gives you the same. Just this one is x0 and this one is x1. So this is swapped, but you can see it. Cool. So that's why we're gonna care about generalizing them, so that we don't want to write like all the components and all the stuff all the time. We prefer to just write a matrix and then assume that this matrix does this stuff. And we can find a condition to what type of matrices are gonna be Lorentz transformations in the following way. So let us start with our invariant interval. We know Lorentz transformations have to respect the invariant interval, and the invariant interval can be recasted like this. Like we know this is true. We can write it like this. Wait, no. We ignore what I just said. Assume this instead. This is better. Okay, I'm gonna just write this down and then I'll talk. Okay, so something I told you is that the four vector, like we have three vectors. Whenever you do a change of coordinates in three vectors, usually you respect the length of the vector because it's a geometric quantity. Like the geometry of the vector is not going to change by what coordinates you're using. So very similarly, when we do four vectors, the length of the four vector is not going to change, which can also be described by the dot product. So the dot product of the same four vector but in different coordinates is essentially the same. And as we saw before, we can use the Minkowski metric to, oh yeah, write this correctly. Wait, let me put it this way. You know, okay. You know the definition of dot product. We could put it like this, but yeah, doesn't really matter. So okay, so you have 2 4 vectors, the dot product. If you remember the definition, you can review it in the review video that I made. This is the definition. Cool. And we can use different indices just so that we can distinguish the indices. This one is in the S prime frame and this is in the S frame. Okay, so you agree with this equality. That's what matters. Cool. So now let us use this fact that we learned here, that whenever we do a Lorentz transformations, which is, this could be a Lorentz transformation, we can multiply by a matrix. So we can use that fact. Let me put it here. Cool. It's gonna be alpha. It's gonna be nu beta x prime beta. Okay, so this is true. We're just using the equality above. And then we can reorganize the stuff. We can make it look pretty. So let's put it in this way. Okay. Yeah, those lines are because we're charging, but yeah, don't worry about those lines. So you see, this side of the equation is the same as this side of the equation. This side. Those 2 sides are equal. So the thing that's to the left, the other factor, has to be equal. This part and this part have to be equal. So let's make those equal. Oh my goodness. Okay, my tablet is struggling. Wait, let me see. Okay. So there's a L nu alpha L nu beta beta alpha beta. Cool. So we have this. We can also just move this one here. I'm just moving this factor here to make it look like matrix multiplication. If you don't see that this is matrix multiplication like outside, just trust me that whenever you see this combination of indices, like 1 up, 1 down, 1 down, 1 up, like specifically with a matrix in the middle, then this can be also written in matrix form like this. Eta. Cool. And we know the matrices, how they look like for eta. And we want to know how the matrices for the Lorentz transformations are. So we can take the determinant. We're going to derive a condition. Determinant. And if you remember for linear algebra, you can like do this. Whenever you have a fact products of determinant, or like the determinant of a product of matrices, you can separate it. And then it's going to be the same as this. And these 2 determinants, like the determinant of the transpose, if you really remember what is the transpose, let's say we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9 matrix. You do a transpose, and then you get 1, 2, 3, 4, 5, 6, 7, 8, 9. Just remember. Okay, cool. So these 2 determinants are going to be the same. You can prove that. We're going to do it. So it's going to be the determinant square of L. It's going to be equal to 1. Therefore, the determinant of L, like any Lorentz matrix, has to be plus or minus 1. Cool. So this allows us to know what type of matrices could be a Lorentz matrix. That's an important condition. And also allows us to divide the Lorentz matrices, the Lorentz transformations, into 2 categories. Lorentz transformations. Oh my god, I'm struggling. Okay. So we're gonna have determinant equal to 1, determinant equal to minus 1. These are gonna be all the boosts that I told you. That is just adding speed. When you're moving to another reference frame that has some speed with respect to you. Rotations. If you rotate your frame, then it's also determinant plus 1. And time reversing, which is when you just put a minus sign in the time component. And then for the parity, for the determinant with for the matrix with determinant minus 1, then you get this is only the parity transformations. And parity transformations basically spatial reversing. Cool stuff. Okay. So that allows us to divide our, like, to know in which category could be a Lorentz transformation. And then now let's continue with relativistic energy and momentum. There were like some technical problems, but solved. Okay, momentum. Cool. So for this section, I'm just gonna give you a bunch of formulas that you might know, might not know. I'm gonna give you a brief explanation, but I'm not gonna go in detail into the derivations, because there's a lot of derivations in this section. And first, let's start with how energy changes. Basically, you just add a Lorentz factor in front of it to the rest mass. This is what we call the rest mass, this part, rest mass. So whenever the Lorentz factor is 1, that means we're at rest, like when the speed is 0. So that's how we get mc squared. That's a way to get Einstein's equation, yeah, like E equals mc squared. Cool. Okay. So the second thing we're gonna see is the relativistic momentum, like how the momentum, normal momentum changes is the same. You just take a Lorentz factor, it works out. Cool stuff. Then we're gonna do probably the most important formula in special relativity, maybe. It's called the fundamental relativistic relation, or also known as FRR. I don't think many people say FRR, but yeah, it's just an equation that allows you to relate the energy and momentum of a particle, and it goes like this. And it's also known as it's just Einstein's equation but extended. So if you make momentum 0, then you get back mc squared. Cool. Then next definition is gonna be for momentum. The for momentum is defined the following way. This one is just really important. So it's gonna be for momentum has 4 components, has any form of 4 vector, and we can define it. The first component be E divided by c. Why? Because of units. So we're combining energy and momentum into one object. And the second component is the spatial momentum. Or I can also write the components like P1, P2, and P3. Or you can also say Px, Py, Pz, whatever coordinate system you're using. And cool. So that's the for momentum. Super important. By the way, a recommendation I have for the class is whenever you're taking one of my lectures, I recommend you to have the lecture notes open with you, because basically what I'm saying is the same that's in the lecture notes. And also, yeah, it allows you to follow better. And yeah, that's cool. Then next thing, we can prove an important identity using the 4 vector, and we're gonna use some Einstein summation. So if you remember from Einstein summation, then we get the first component squared with a minus sign, plus the second component p squared, or like this component squared. Just Einstein summation, which if you use the fundamental relation that we just put here, the fundamental relativistic special relativity relation, then you get minus m squared c squared, which means that whenever you square a 4 momentum, or just take the dot product between 4 momentum, this essentially is always going to be equal to m squared c squared. Cool. Very important in some classes. I don't know why professors just like to ask this random fact, so you can answer this. It's always going to be minus m squared c squared. Cool. Now next section is going to be proper time, and we're going to use proper time. We're going to define it right now. Cool. So essentially what proper time is, we want it, like, consider that we have a moving particle, like some particle that has some trajectory. We can describe it using the 4 vector and a parameter. This parameter, I think I told you last lecture, is something that allows you to map, like from here. Let me move this. Let's say we have our path, and then we have like a straight line that is just the real numbers, and each timestamp, or like proper time stamp, allows you to parameterize this curve. So you can just do then this one goes to the next one, and so on. That makes sense. Cool. So how is proper time defined? Proper time is a measure of time, like is the particle, whatever particle is traveling this thing, this path, on time. Imagine the particle has a clock, like a very fancy clock, and this clock is measuring its time in its frame, like its frame of reference in which is stationary, that's proper time. Cool. What I have in the notes, I think will make more sense. So we know different observers record different values for a time interval. Different time interval. But if we have this particle that has a clock and is moving around, then the proper time is defined as the time that passed in the particle's clock. Yeah, as the time elapsed, or time passed in particle's clock. By clock, I just mean frame of reference. Same words. And the important thing of the proper time is that it's an invariant. So whenever you change frames, like any other observer should agree on like what is the proper time of a particle, like what is the measure of time in the reference frame of the particle. And it's an invariant. We're gonna show this. Invariant quantity. So whenever you change frames, the proper time is not gonna change. Cool. So now, remember our invariant interval that we mentioned before? We're gonna get rid of the x, the y and z components, and let's consider only one dimension. Okay, cool. So if we have a particle moving, we know we can just say that this is b times the time interval that is moving. It's just the speed times the time interval. So we can replace this. It's gonna be b squared dt squared, and I can take out a c factor from here. Let me take out minus c squared and also dt squared. So then this is gonna give us 1 minus b squared over c squared. And if you remember, b squared over c squared is just beta squared. So beta squared, cool stuff, right? And something that we can see is that whenever we're in the particles frame, so in the proper times frame, particles frame, same thing, then the particle is not moving, so everything else in the world is moving to you. Like imagine it's like a very, I don't know, you're the center of the world and everything is moving past to you. So that's your frame, your relativistic frame. So yeah, so in this frame, nothing else, you're not moving, everything else is moving, and we can call your time proper, like dtp, which stands for proper time. So in this frame, since you're not moving, then the speed is 0, then beta 0, cool. Therefore, we have that minus ds squared is equal to minus c squared dtp squared. So a good definition for proper time is ds over c, which is the invariant interval, which is an invariant quantity, divided by c, that is the speed of light. So invariant quantity divided by non-invariant quantity is something that is not going to change when you change Lorentz frames. That's why the proper time is an invariant quantity. Cool. Pretty useful. And if we go to a more general frame, like not necessarily we are in your frame. Let's go to like Bob's frame or whoever's frame. Let us go back to this part. Okay. I'm just going to copy this line. C squared dt squared times 1 minus beta squared. Cool. And this was equal to minus ds squared. Let's take out this minus sign. Cool. And let's take a square root. I'm gonna get dt. Okay, this looks weird. Okay. Square root of 1 minus beta squared. And if you remember from our definition of the gamma factor, then this is just gonna be the gamma factor. We're gonna put it there, do some algebra, and then we get this relation. Then how any time relates to the proper time. This is one, like how a general time relates to the invariant interval. And if you remember from our definition, ds divided by c, so if we multiply by c in both sides, then dt related to a proper time is just gonna be the gamma factor. So that's another definition for a proper time, like how much it changes with respect to any other general time is gonna be just the gamma factor between these two frames. Gamma factor, like, just remember, definition. 1/1 minus b squared over c squared. That b, okay, cool. Cool stuff. So this proper time is gonna allow us to define what is a forward velocity. As you can imagine, it's just taking a derivative of the position for vector with respect to the proper time. And this can also be written as like c times dx mu divided by, or like taking the derivative of the with invariant interval. This is the forward velocity. And the funny thing with the forward velocity is that you can write now the forward vector in terms of the forward velocity as we did it usually for the normal forward vector, or like for the normal momentum. Cool. This is very analogous to the usual formula, mb. Cool. Same thing. Great. So that's all for special relativity for now. Now let's go into classical mechanics. Now let me put a new section here. So chapter 3 is going to be classical strings. Cool. Okay. Now let's take out our hat of special relativity. There's no more stuff like time dilation, length contraction for this lecture. Next lecture we're going to come back. But for this lecture, just introduce you to strings. Let's go back to F equals ma, Newton's equations, very classical stuff. Okay. Let me change my notes. Okay, so why we care about this? We're describing strings. We want to understand the simplest string. And we're going to use, instead of F equals ma, we're going to use an equivalent formulation, like equivalently, that is called Lagrangian mechanics. Anything that you can do in Newtonian mechanics, you can do it with Lagrangian mechanics, and vice versa. So this formalism has a lot of math and abstract stuff that if you want to see in detail, you can take one of the many classes that there is of classical mechanics, intermediate mechanics. There's probably a Meki class on this. Probably other majors have these type of classes. But for now, I'm just going to introduce you to the basics, and you're going to have to trust me on most things that they're true, because the derivations are pretty lengthy. Like usually these derivations would take 2 classes. So I'm just going to introduce you to the main concepts. So first, what is a Lagrangian? Okay, so the main thing in this, before we start with specifics, the main thing in Newtonian mechanics, Newton and Lagrangian, so here were forces, and here is going to be the action. Like the action is what's going to matter. We're not going to talk anymore about forces. We're going to describe everything by an action. And the action you can calculate it using Lagrangian. So that's why it's Lagrangian mechanics. And based on the action, from here you can derive equations of motion, which were like the, like whenever you get x equals pt, this kind of stuff is the equation of motion. That tells you how your particle moves in time. And with forces, you were also able to derive equations of motion, which was using F equals ma, or equivalently we did pp dt. Is it right? I hope that's right. Okay. Dx squared dt squared. Okay. So that was the usual formulation. We're not going to use this anymore. We're going to use this new one. And trust me that they're equivalent. Cool. So the definition of a Lagrangian. A Lagrangian is just going to be defined as the kinetic energy minus the potential energy. So kinetic energy, we're going to try with a T. I don't know who gave this notation, but it just stick forever. Minus the potential energy. That's the definition. Cool. Now, the action. Second definition, the action is going to be defined, and this is like the main quantity of this whole chapter. It's gonna be a functional. If you don't know what a functional is, you're gonna know it after this lecture. So it's defined as just the integral of the Lagrangian in a time interval. So you have a path. So take any path, integrate over that path on the Lagrangian, and then you get the action. And why is it a functional? A functional, the definition is very simple. You have some function, let's say this f. You take a function. You're gonna take a function, for example, a path. A path is a function, and this is gonna give you a number, like something like 8, 9, some number. So that's the definition of functional. Take a function, give you a number. Cool. An example of a path. I can draw this. We have t, we have time. Forget about space-time diagrams. This is just a normal x and t diagram. We have a path, something that's here. Let's call this a path. It starts as a position ti and position xi and time ti, and it finishes. I didn't draw that, but you know, xf tf. Cool. That's just path. You integrate over that path, and yeah, you can also, instead of writing like this, you can say tf normal integral. Cool. Okay. So second important thing in Lagrangian mechanics, we just gave 2 definitions here. The third important thing, Hamilton's principle. Oh yeah, something important, might be important, is that the Lagrangian is a function of time implicitly, but the action doesn't depend on time. So that might be important later. Okay, so Hamilton's principle just tells you the following. I'm just going to state it. The path or the equation of motion the system will take, like whatever your system is described by the Lagrangian takes, is when the action is stationary. Action is stationary. And by stationary, I just mean that is, I'm gonna put here, that it doesn't change. It's not change to first order. I'm gonna give you an example so that this makes sense. Equals 0. So the equation that's gonna describe all Lagrangian mechanics is this: that the action to first order is not gonna change. Equals 0. Cool. So in order to understand what the symbol is effectively a derivative, but it's a variational derivative. So now we're gonna learn variational calculus. Cool. Or calculus of variations. Calculus of variations. And this is gonna take most of the lecture. We're gonna do some computation on some examples to make it clear. Okay, so we're gonna do a simple example. Let's consider a particle dot that has some mass. We're gonna have mass m, and it's moving along the x-axis. Along x-axis under bx potential. Okay, you remember from whatever mechanics class you took, then the kinetic energy is just mp squared, which can also be written as mx dot squared. Dot just stands for this, for the time derivative of any quantity. So whenever you see a dot, that's going to be a time derivative. Cool. Then potential energy. Potential energy is just going to be rbx. They already gave us the function, so it is bx potential. Okay, cool. We have everything we need to construct the Lagrangian. So combine these two, then you have 1/2 mx dot squared minus bx. Great. Okay, so the action over some path is just gonna take the following form. It's just gonna be ti. We said that's just the time integral over the Lagrangian. And our Lagrangian is this. This looks like a funny, complicated integral, right? So for any particle, this is gonna be the action. And now we need to know how to find a path. Like, how do we find the path that the particle is gonna take? We said that whenever this is true, then that's gonna be the path that the particle takes. But how do we do that? How do we use math? What do we do? Cool. Okay. So Here we're gonna use method 1, that is just using pure calculus variations. So first let me do this. Let me take the action, this same action. Let me just put here that this was a functional. These brackets just denote a functional, helps you to distinguish between a functional and a functional. But essentially both are functions, so it's okay. Okay, so important. Let's consider a path, any path, and a variation. A variation is just some little difference between the original path and the other path. For example, a variation of this path could be something like this, something that changes a bit. Let's say that's infinitesimal. That's the whole thing of variations. Instead of doing like calculus when you change by infinitesimal amounts, then you're changing a path that can be more dimensions by a little bit. And in this case, we're changing by delta x. So we just replace, instead of x in the formula, we're gonna replace by x plus delta x, and that's gonna give you this. Half m d dt x plus delta x. I'm just replacing. If you already know all of this, you can low-key skip it, but might be useful to remember because we're gonna do like, usually in 301, they don't teach you like the pure calculus variations, and that we're gonna use for most of the class, so good to review, good to know. Okay, so then we can just do the following, dt half m. Here I'm just gonna use the dot notation, x squared to x delta x dot plus delta x squared minus bx. Here I'm gonna use Taylor expansion. If you remember what a Taylor expansion is, here you go. So Taylor expansion of this to first order, it's just gonna be bx plus the first derivative and delta x. Cool, Taylor expansion. Okay, next thing, we're gonna neglect this term because we only want to calculate first order. This is only first order, so we don't care about second order right now since it is infinitesimal. So it's that's 0. Just neglect it. We don't care about it. Then you can reorder this integral to 1/2 mx dot squared minus bx. I'm just moving terms around. Plus m dot, wait, let's see, mx dot times this x minus bx prime x. Okay, let me check this right. So here we have this term, then we have this term, then we have this term. Cool. Okay, we have all the terms and we neglected higher orders. Great. So you can notice this is the original action. If you look at here above, it's the same thing. Cool. And then we found what is the variation. This is the variation of the action. So we can identify this as delta s. And as you remember, what is the variation of delta? Delta s has to be 0. That's the whole thing of Hamilton's principle. If you want to find equal motion classically, delta s equals 0. Cool. So now, let us write delta s. Delta s is going to be this. Tf, ti, mx dot, and then delta x dot minus b x delta x dt. Okay, so here are two roots. You can do, if you know how to do this, you can do integration by parts. But if you don't know, let's use this fact. This is a trick you're going to use many, many times, and it just takes time to get used to it. So usually it's just, okay, let me write it and I can talk about it. So this is what we're going to use. dt. Let me write instead of this dot, let me put this explicitly. Okay. This is going to be equal to the following. So essentially what we're going to do here is combine everything inside the time derivative so that we can do some simplifications later. And how do we do this? So usually the way to do it is you write everything inside the time derivative and then you assume, okay, and you don't assume anything. You just write everything inside the time derivative. You take the product rule of the time derivative, and then there's gonna be some extra factor. This extra factor is gonna be mx dot dot delta x. If we do here, like if you just do the product rule here for this derivative, you're gonna get this factor. So you just subtract that. Therefore, your original, this original factor is gonna be the same as this time derivative minus this extra factor. That's gonna be the trick. You're gonna use it many, many times to do any type of, like whenever you get an action, you wanna take the equations of motion, you're gonna do this all over again. So cool, just to remember. Remember this type of trick. It's not gonna be the same, it's just gonna be, you put everything inside the time derivative, do the product rule, subtract whatever is not in your original term. Cool. Okay, so let's use this fact now to write our action, or our variation of the action. So this is gonna give you this dot x minus mx dot dot delta x minus bx delta x dt. Cool stuff. Okay, so next thing we're gonna do is make this equal to 0. So we know delta S by the Hamilton's principle has to be equal to 0. Cool. Let me check if this is right now. Good. Okay. So for the first term, you can just use the fundamental theorem of calculus, derivative, integral. You can just subtract those two. So wait, before we make it equal to 0, this part is gonna give you two terms. Just evaluate TF, delta x, TF, minus mx dot TI, delta x, TI. And then the second term is just gonna give you the integral. So TI, TF, delta x. And maybe you're seeing something here that looks similar, looks familiar. So that's good. Okay, so we know the endpoints. Like the endpoints, I forgot to mention this, but whenever you do a variation, you're not changing the endpoints. Like you change everything on the path. You do like little variations on all the path, like every single path possible between these 2 points, but you don't change the endpoints, which that means that delta x, like the variation on the endpoints, is gonna be 0. Since we're not changing this, like this stay fixed. Cool. So bam, bam, these two go away, and then we're left with only this part. So we can make delta s equal to 0, and that's gonna be equal to this integral. TITF delta x minus mx dot dot minus b prime dt. Cool. So this is what we wanted. For every path, this integral has to be 0. So this term has to be 0. And essentially, we just found, like that's Hamilton's principle, we found the equation of motion. And yeah, if you remember from your classical mechanics class, a force can be described minus a potential, or like minus the gradient, or minus the derivative, also known as the gradient of a potential. So then this is equal to, like this is the same as writing ma equals f. So we just rederive Newton's equation of motion. Yeah, cool stuff. So it's just a fancier way to do classical mechanics. I know the math is much more convoluted, but it allows you to do like more complicated systems. Like you don't restrict yourself to you having to know the forces. If you know the energies, then you can know absolutely everything of the system. So that's what matters. Cool. Now method 2, you're gonna use it many times. I want to show it to you because you will be able to use it for some cases, and eventually I will tell you what cases this is useful for. And it's the way that outside of string theory and like in most, like until undergrad level, you're gonna see this being used because it's very convenient. Euler-Lagrangian equations. Even like field theory and advanced field theory, you're gonna still be using Euler-Lagrangian equations, which is just a formula. This formula tells you that the partial derivative of x, or like the Lagrangian with respect to x, minus this. It's just a formula. You just plug in, plug and chuck. That's it. So this formula might be modified a bit in order for different situations, but this is like the main structure. Take the spatial derivative, and then you take the time derivative of the spatial component dot. Cool. How to use this formula in our example? So remember that like the Lagrangian is this. Cool. Let's take this partial derivative. This is just gonna give you mx dot. Cool. And then let's take the other one. Let's do dt. This time derivative, mx dot dot. We're assuming that the math doesn't change. That's cool. And then we take the other partial. This is just gonna give you bx with respect to x. This is just minus b prime. Whenever I say b prime, this is a spatial derivative. Like if some quantity is dot, that's dt. Whenever a quantity is prime, that's dx, or spatial. Cool. Conventions. And then if you combine these two into the equation, just plug and chuck, then that's gonna give you the equation of motion. Yeah, it's much faster, much simpler to derive equations of motion using this method, but there will be cases in which it's just not feasible to do this. I'll show you why when we get to those examples. Cool. Okay, so with this introduction to classical mechanics and how to use it, then we can go into non-relativistic strings. So we can finally start doing strings. Okay. So let's consider a string in the xy plane. And it has fixed endpoints and fixed endpoints. Let's call it 0, 0, like the origin, and a0. Cool. So we're gonna have that the string, the transverse displacement. We're gonna describe it. Transverse displacement. If you taken 201, you already know this, so I'm gonna go quick on this. I think like 80% of you had taken 201, or like some equivalent waves type of string, or no, not string, but the waves class. So, well, you've probably seen it in classical mechanics already. So the transverse displacement is described by the y coordinate. We're gonna use a y coordinate. Cool. Coordinate. I know my handwriting is not the best, but we'll survive, I hope. And there's two pieces of information from the string that we care about. One is the tension, like how much tension you apply to a string, and the mass per length. Essentially the mass of the string. Mass per length. We're gonna call it mu naught. T naught and mu naught. And then the total mass, like the whole mass of the string, is just gonna be equal to mu naught times the length. And the length of the string is gonna be a. That's gonna be the length of the string. Cool. Okay. So if we wanna draw the string, which is gonna be important, let's put this here. Let's put this here. Let's put a string here. Low-key, I could just copy the graph I have in the notes, but you know, I like to draw. Not really, but that's it for now. I like it. Okay, so then we have this small segment of the string that's gonna have like some y plus dy and x plus dx. So this is dx, this is dy. Cool. Okay. So we know, let's assume first that the oscillations are small. By assuming oscillations small, I just mean this condition. Are small. This is gonna be general, but it's gonna allow us to simplify. Right now what we're doing is deriving the equation, the wave equation for a string. So let's assume oscillations are small. That's gonna be that the partial of y, like the slope, is gonna be much less than 1. Cool. So yeah, the transverse displacement is gonna be small compared to the length of the string. Great. And then now let's assume that we're gonna stretch. So let's stretch the string a bit. String at the x. That's what we're doing right now. The x amount. The tension is gonna be the same, so the tension is just gonna stay constant. It's constant. And now I want to calculate the vertical force. We want to calculate like what's the force on the string, like what's the vertical, horizontal force. There's a tension here, and yeah, cool. So there's tension in both sides of the string. So to calculate the force, we can just do what is the tension multiplied by sine of theta. There's some angle here, like between this here, some angle. Theta of sine. And since it is the small angle approximation, this is the same as tangent, because you can imagine that cosine is almost equal to 1, so you can just say it's the same as tangent. And what is the tangent? Is the slope. So the slope is delta y, delta x, like just the partial derivative of y with respect to x. This is the slope of this slope, and this is evaluated at x point. Cool. And then the full vertical force then on the string is going to be the following. That's one of the components. So if you take the small segment, then you can evaluate the vertical force at the x plus dx part minus the vertical force at the x part. If this doesn't make that much sense, we're using a derivation. This part is not completely important, but if you follow it, cool. So this is just the definition of the second partial derivative, if you remember from calculus, which is going to be t naught squared, t naught not squared. Second partial with respect to x squared and dx. Why this dx? Because we didn't have 1x here, so we just want to add. Like imagine dividing this by x and multiplying by dx, and then you can take the second partial derivative. Okay, so now we can use Newton's law. So Newton's law is going to tell us there's going to be some small acceleration here, like some dm, and some vertical acceleration. Cool. And we can recast this in this form. So the left hand side is just what we found here. That is the second partial derivative dx. And the right hand side is the mass of a small piece of the string, which we had the linear density of the string multiplied by this small piece. And the acceleration is just going to be the second partial derivative with respect to time. And essentially, what we just found, if we reaccommodate the terms, is the wave equation for the string. Cool. This is for a classical string. So if you have a string, your favorite string at home, you can use this equation to describe it. You just need to know what is the mass per length of the string, and also the tension of the string. So this is just a wave equation. If you remember from 201 or any wave equations class, or partial differential equations, I don't know. This is the original wave equation. Or if you didn't know it, now you know it. So then you notice that this term is the same as this. Therefore, the speed of this wave or string is just square root of the tension divided by the linear density. Cool. For relativistic strings, this is going to change. This is just for non-relativistic strings. Relativistic strings. Okay. So we have a wave equation, or also known as an equation of motion, that describes your system. And you want to solve it. But first we need to impose some boundary or initial conditions. This is a second order partial differential equation with two variables. These two variables x and t. So you need an initial condition for time, and you need a initial and a boundary condition for space. Cool. So this is gonna be a very important part, not for now, like this is gonna be important to know, because then it's gonna generalize to general strings, and that's when it gets funny. So let's start with boundary conditions. Boundary conditions. There's gonna be two types that we're gonna care a lot about. One is Dirichlet boundary conditions, and the other one is Newman boundary conditions. Cool. Just remember, we're just defining what they are. So at some time, and at the first point is equal at the last point, it's gonna be equal to 0. So basically it's telling you that the string is fixed at the endpoints. They can be fixed at some point. It doesn't have to be, but it's just some constant. So it can be 0. And I'm gonna show you a picture of how this works, so you have like a more clear intuition. Cool. So in this case, it's at some time, and these are gonna be 0. So this is there's rings at the endpoints. Yeah, from the equations, this is okay. Strings. Okay, the picture is gonna solve it all. Trust me. So let's assume xy. We have xy here and xy here. So you have strings attached at the endpoints. It doesn't have to be this specifically endpoints, but some endpoint. Here I put 0, but this is a Dirichlet type boundary condition that you have the string fixed at the endpoints, and there's like some wall here. You can imagine there's a wall that is fixing the string. While in the other case, let's assume there's a wall here and there is a wall here. And instead of fixing the endpoints, we're fixing the first partial derivative, which means that there's a ring here. There's a ring and there's a ring here. And basically the string is just moving. It has 3 moving endpoints, which just rings. Cool. So that's for boundary conditions. We have these two types. And now we go for initial conditions. These ones are in time conditions. Okay. So remember that the wave equation has a general solution form of this type. Or trust me, if this is not a known fact, that you can like make a wave equation out of 2 other waves. Or like you can make a wave out of one wave going to the right and one wave going to the left. Then this is the wave going to the right, and this is the wave going to the left. You can imagine that's a standing wave, and standing waves can describe strings, so that's cool. This one is right moving, right, and this one is left. Cool. It's just a function. And now we're gonna show what are these functions. Okay, so suppose we know the initial values of y, we know all these initial conditions of partial yt at time 0. So then we can solve for these two functions, this one and for this one. Cool. That's how initial conditions work. You can plug them in and solve for stuff. And yeah, this gives you 2 equations. We're not gonna solve the equations, but I wanted to show like how you in practice would solve the wave equation. Great. And now let me give you an example. Is it worth going to example? Yeah, sure. Let's do a review of how you get the frequencies for a wave. So assume there's a solution of the form. Let's just have an ansatz. Let's call this an ansatz. We're still working in the wave equation, just to make sure we're on track here. So there's an ansatz that there's some amplitude that might change depending on position, and we have a sinusoidal. You have a frequency, time, and a displacement. Frequency and a face. Cool. Okay, so we can substitute this solution in the wave equation, and we're gonna find, I'm going through this very quickly since it is not the most relevant, but we're gonna find this. This is what you get from the wave equation for the amplitude. And then we can use, let's say we use Dirichlet boundary conditions. Then you can find solutions of this type. You know how to solve differential equations. Most of you, if I can do a reminder on this. This one is not as important. So with Dirichlet boundary conditions, you find the following: that there is some constant, some index, and it's just assigned. And it has many solutions. 1, 2, all the natural numbers. And we find different solutions for Dirichlet boundary conditions and Newman boundary conditions. That is the point I want to make, that you find different solutions depending on the boundary conditions that you have. And that's essentially like what is the geometry of your system. And that's going to be very important when we go later. And for Newman boundary conditions, you're going to find the solutions. N cosine n pi x e. Cool. And let's say we plug back this into this equation, into our equation that we derived from the original equation. Then we can find that the allowed frequencies for our mode to oscillate are going to be square root of T naught, U naught, and pi over A. I might put this as a second exercise because I wanted the first to be calculus of variations so you can practice some calculus variations. And yeah, that's cool. Okay, so these are the allowed frequencies. And like the allowed frequency is going to be very important when we do quantized relativistic strings, because that's going to tell you like what particles you can actually have in your system. And it's going to be like the whole mambo jumbo of string theory leading to the standard model, and cool stuff. Okay, so we're done with this little example of a string and how to use boundary conditions and initial conditions. So now let me show you, instead of doing like this, because we use Newton's equation here. We did like F equals ma, then we derive the equation. Now let's do it with Lagrangian mechanics. We learned Lagrangian mechanics for something, right? So let's do a Lagrangian version. Lagrangian classical string. It's the same, but it's gonna be much faster. Okay, so the kinetic energy is gonna be equal. We're gonna have to integrate. Okay, let me write the formula and let me show you why this makes sense. Okay, so you remember the kinetic energy is equal to 1/2 mv squared. So this is the mass for a small segment of the string. This is the speed squared, just written in derivative form, and 1/2. We integrate over all the string, and that's gonna be the whole kinetic energy that the string possess. Cool. So then, for the potential energy, we can calculate it in this way. You can take a look at the earlier picture just to remind of the notation. Take a look. Cool. Okay, so we have the difference in length or the stretch, which is gonna be equal. We want to calculate the work. That's what I'm doing this. So we have this 2 minus dx. So this is how much the string stretched compared to the original length. So we can do this. 1 plus partial x squared minus 1. And since we have small oscillations, remember that this factor is going to be much less than 1. So then this is going to boil down to dx 1/2. Now I'm doing first approximation here. So x squared. Cool. Here, remember that the Taylor expansion of this is 1 plus 1/2 times square x. Yeah, that makes sense now. So this is just the Taylor approximation. That's gonna give you this. And since we know now how much the string is stretched and how much the length changed, we know from the work. That's gonna be T naught times this stretch. Like this is the force and this is the distance, force times distance. So essentially, you can say that the potential, like what is the whole potential energy of the string, is gonna be essentially this. Just adding up each small segment. Cool. And there's a T naught here. Okay, so now we have the potential energy and the kinetic energy, and we can construct the Lagrangian. The Lagrangian is just gonna be one subtracted from the other. So then you get this. T squared minus 1/2 T naught. And essentially what we're doing now is called classical field theory. That is when you have more than one point in space and you're doing classical mechanics, cool stuff. And we're gonna define this inner part with this fancy symbol that is like an L. And we're gonna call this L Lagrangian density. Because you can imagine the Lagrangian is that whole integral, and then you integrate over what is inside the integral, and this is like the density of Lagrangian. So yeah, so you have like an integral or a density. Cool. Makes sense why the name Lagrangian density. And yeah, from now on we're gonna see only Lagrangian density. It's gonna be like the main object of study, because every system is gonna be a continuous system. So that's cool. And we can rewrite now our Lagrangian like this. 0 to a, Lagrangian density, dx. Cool. So for this, for the classical string, the Lagrangian, it's gonna be this. And now sometimes when I say the Lagrangian, I just mean the Lagrangian density. Cool. Great. Okay. So then we can write the action. We can write the action in the following way. Let me simplify my writing. Okay, let me write the action. The action, just remember that is the integral of the Lagrangian, or it can be the double integral, first time integral and space integral. Or let me swap these two integrals. That's okay. A and 0. So there is time, there's a space of the Lagrangian density. Cool. So that in this way we can simplify stuff. Okay. And then let me replace the Lagrangian density just here with all of this mumbo jumbo. There you go. Cool. Okay. So if you remember how we did the derivation of the equations of motion previously, what we did, it was taking original action, we do the original path, and we add some variation. And then we want to get delta S. Then we want to make that equal to 0. I'm not going to go through the procedure because it takes some time. Wait, is it worth it? You know, let's do it. But basically you would take this part, you plug it in, you will recover the original action plus some component, as we did before. Like here we plugged in the original path plus some variation, then you recover back the original action plus some variation. So we're gonna skip that step because you just plug it in and like reaccommodating terms, and maybe using the product rule that I mentioned is very important. And from there you can get the variation. So I'm just gonna write what is the variation. So the variation is gonna be this. 0, not. Then there's a partial, there's a delta y, it's a t, minus t naught, y, x, delta y, delta x. Cool. Okay. So now we can use the trick I told you to rewrite each term as a full derivative. Like you put everything inside the time derivative, inside here. And then you subtract whatever you get from the product rule. So we can do that. Let's do that, and we find this. I'm not gonna do it in detail. I'm just gonna put the result. But yeah, put everything inside the time derivative and subtract whatever is left from the product rule. Okay, so in this case, what we get for product rule is this squared x minus t naught is y x y. This is all in the lecture notes, so don't worry if you're not copying something. Alright, cool. So then we can separate, like we can use these integrals that we have here to separate this into two terms. The first term is going to be the following. Okay, let me write this down and I'm gonna comment on it. Okay. That's the thing of calculus variations. Like it takes a while to compute stuff, but I don't know. Once you get the trick of like the two things you have to know to compute stuff in calculus variations, it gets fun. I'm gonna put an exercise, like the third exercise is probably gonna be doing the whole derivation for this, if you wanna have some fun. Okay, there's this, and there's gonna be also minus here, and there's gonna be stuff that's left. Ti 80 dx minus t naught. Cool. Okay, so we're gonna say this, the variations of the endpoints of like ti as before are gonna be 0, since whenever we do calculus variations we don't vary the endpoints. Great. And then for, and like this is gonna be true only for Dirichlet, so this is true for Dirichlet, we're fixing the endpoints. But in Newman boundary conditions, if you remember, then the endpoints can vary, but we impose the following. We impose that this should be true. That wait, one of my derivatives, this one is wrong. Oh. So the spatial derivative has to be equal to 0 at the endpoints, at x equals 0 or a. Okay. So this is gonna lead to the second term vanishing. Like choose one of the two, like whether you choose this one or you choose this one, then the second term is gonna vanish, because either this vanishes or this vanishes. So cool, we get rid of the second term. Then yeah, wait, let me, oh yeah, something I forgot to mention. So this is x, xi, and xf. So this is spatially, like boundary conditions are spatially, that's my bad. And also, like, what is always going to be true is that in time the variations are gonna vanish regardless of Dirichlet or Newman boundary conditions, because this is on time. So because this variation is gonna vanish, then the first term is gonna vanish always, and we're left with only the last term. So let us write the last term. The last term is just gonna be this df dt 0a dx not partial. I'm looking at the time. I think I exceeded time too much, so let me do one more thing and then we're done. And then y. And okay, same trick. Hamilton's principle tells you that whenever you have the variation, then you can make it equal to 0, and for every path, for every variation, this thing has to vanish in order for the full integral to vanish. So we found the equation of motion. It's gonna be the same argument. So once you do 2 examples of how this works, you understand the trick, and like it's gonna be easy to do the whole course. But yeah, I'm gonna put like probably two exercises on calculus of variations in the problem set for this week. So cool. Okay, so another convenient way to write the boundary conditions is just gonna be the following. These are the formulas you are actually gonna have to remember. Trust me, that is equivalent. Like Dirichlet's boundary conditions is equivalent to writing this. That the time derivative, like when the time derivative is 0, then that means that the endpoints are fixed, they cannot move. So that's Dirichlet. Instead of having to fix the endpoints to some value, we prefer to fix the time derivatives to 0. It's more convenient. And for von Neumann, it's just the same. It's just the same as we wrote before. TA equal to 0. Cool. So just remember these two formulas for Neumann and Dirichlet. And they're kind of intuitive. But you have questions, let me know. And let's see how much time we have. Okay, I'm gonna extend this a bit. I want to finish. This is the last thing for classical mechanics. And once we finish this, then we can get into relativity strings next week. We actually started fun stuff. You're gonna see a lot of funky stuff happening. And one of the funky stuff is actually D-branes. We're gonna do a hint. We're not gonna do D-branes. Like what D-branes, where D-branes come from. We don't know what D-branes are yet. Like, I know what they kind of are, but you don't know, guys, yet. So, okay. Let me first calculate the string momentum. I'll do it very quick. Okay. So you can trust me. This is mass, this is the mass part, and this is the B part, mass, B. And now we want to see if this quantity is conserved. So let's take a time derivative. You can take the time derivative inside the integral. So you have 0a dx. Cool. Now I can use a relation between the speed. Wait, let's see. Here I can use the wave equation. So if you remember the wave equation that was here, we can use it here to change this into this integral dx. Okay, cool. So then this is gonna get you this. Basically here we're just canceling this part with this part. Yeah, this is physics math. If there's a math major, don't hate me, but that's how we work. And essentially you have an integral over a derivative. So that's just, we're just gonna evaluate, take the, like by the fundamental theorem of calculus, we can evaluate this integral at the endpoints. So here's the thing. Here's the, like this was puzzling, like let's go 50 years ago to the first string theorists, or like what's going on, bro? So for Neumann boundary conditions, the momentum is 0. Which means that this quantity is 0, because this is just the speed, like this is mass times velocity. Cool. So this vanishes at the endpoints. Like for Neumann, this was a condition that we imposed, or more specifically this. I don't know why I wrote this in the notes. Okay, don't trust the notes sometimes. Trust them almost always, but not for now. So at the endpoints, this was true. That this quantity vanishes. So this was 0. That was okay. So there's vanishing momentum at the endpoints. That's good. But if you do Dirichlet, this is where the D comes from. If you watch One Piece, this is the legacy of the D. Nothing to do, but you know, if you know, you know. Dirichlet. Cool. Okay. So let's do the same. Here at the endpoints, if this quantity doesn't necessarily have to vanish, like there's no condition of like this thing has to vanish. So therefore, the momentum is not conserved. Like at the endpoints, dp, oh okay, I know, dp dt. So here, like in Neumann, momentum is conserved. But when you have Dirichlet boundary conditions, which means fixed endpoints, then the momentum is not conserved. This is gonna correspond to a closed string, or to strings with fixed endpoints, and it's gonna correspond to strings with free endpoints, like they can just move around. So the momentum is gonna be conserved. But then when you fix the string to some wall or to something, then it turns out and the momentum is not conserved. That's crazy. So what can be, like, if the momentum is not in the string, then where is the momentum? That was the question. That was the question that maybe people were asking. And people didn't know. So eventually, someone proposed, well, what if there's this object called a D-brain that's actually taking this momentum away? In this case, in the classical string, this is the wall. Like we know the wall is taking the momentum. Like the momentum that is not in the string is gonna go to the wall. Cool, that's cool. But if you go to small strings that there's nothing else in the universe than strings, then what's going on? So we're gonna show these D-brains. I think it's gonna be lecture 8 or 9, around there. And we're gonna study them in very detail. Cool. Then there's another derivation of the string equation of motion that has some notation. Let me just give you the formulas. We're not gonna do this derivation because it's the same thing, just using Lagrangian mechanics. Because we did that twice already today, and we're extending over time. So just remember these formulas. I'm gonna make clear what these mean eventually. Just look at them, remember them for now, and yeah. And the equation of motion of the string can also be recasted like this is string equation of motion. Classical string can be recasted in this way using this new definition. So this is, we're just defining new objects. These are eventually going to be momentum-like stuff, and we're going to analyze it in much more detail next lecture. So thank you. I hope you stay warm, and I think I exceeded so much the time, but I'm going to put like cuts. And if anything of this doesn't make sense, I have office hours on Fridays from 2 to 3. My office HBH, it's only a syllabus and in the announcements. So take a look at that, do the homework for this week. And this homework is gonna try to make it easier. It's gonna be more like, this is stuff that we today, so you have all the stuff you need. Okay, next week, relativistic strings. Cool.